This last lecture of Module 2 is about centrality and similarity in graphs. To situate where we are in terms of the larger course objectives for the semester, remember that last time we talked about being able to extract graph structures from web data. And then we talked about graph analysis methods, specifically about PageRank. This time we're going to continue the discussion about graph analysis with a number of new techniques. So last time we talked about PageRank. This time we're going to be understanding some metrics for evaluating importance of nodes in graphs, as well as some methods for doing clustering in graphs and evaluating similarity in graphs as well. So there are four main main objectives for the lecture today. The first is to describe at least three network centrality metrics. I'll give you a number of them. Then using the betweenness centrality metric and the Girvan-Newman method to identify communities in graphs. You should then be able to construct bipartite graphs and then understand and describe how random walks, especially in bipartite graphs, give us a way to measure similarity of nodes in these graphs. So just to rehash, remember from last time we talked about how the web is full of networks. In particular, a standard example is the connection between political blogs and the blogosphere. But the question came up about what does this have to do with the web? So understanding something about graphs and networks in general, how can we use that in the web? And the main question we tried to address was how we use this information to organize the web for search, to make the web more accessible and more useful for people who want to find information therein. And this really boiled down to two main tasks. The first is finding relevant web pages, the standard thing you may expect with a search engine, but also finding trustworthy pages that actually are useful or authoritative sources for information. So how do we find that? And we introduced PageRank by Larry Page and Sergey Brin from Google as a solution for this, where recall that the PageRank idea is that given a large network of websites or web pages that link to each other, we use PageRank to evaluate or come up with a metric that is approximately equal to the likelihood of stumbling across one of these sites based on a number of random walks or random explorations throughout the internet or the World Wide Web. So if you were to fall on some random web page somewhere and then click randomly throughout this web network, where are you likely to fall? And the more likely you are to land on a particular page, i.e. the more links that go to that page, the higher your PageRank score. So you could imagine what the example we went through was places like YouTube and Amazon have a very high PageRank score. Places like Reddit, Facebook, and Twitter have a high score as well, but maybe not as high as YouTube and Amazon. And there are many, many pages that have a very low PageRank score. And the idea that a page's particular PageRank is some combination of the PageRanks of all the nodes or all the web pages that point to or link to that particular page. And we look at this in terms of a directed graph where one page links to another, but just because one page links to another doesn't necessarily mean that the second page links back to the first. We talked about how we use this from an information retrieval perspective, or how we can use this in our search engines. So for an example, say we search for Amanda Gorman, the Youth Poet Laureate in the United States. We can look for or find websites that have the query Amanda Gorman in them, such as her Wikipedia page or her personal page, but we also may find maybe less desirable pages like t-shirt sales stores where somebody has embedded the words Amanda and Gorman into those pages a great number of times, even though it has really nothing to do with, the website has nothing to do with Amanda Gorman, but the idea is the search engine is being exploited in some way to drive traffic to this website. So by using PageRank from Google, the idea is we can take these three websites and then sort them according to their PageRank. So we can show you the website with the highest PageRank first, and then the second highest PageRank, and so on, under the expectation that these less authoritative or less trustworthy pages have much lower PageRank scores and end up very low in the search results or the rankings. So from a high level, we can ask, what really is PageRank? In some sense, we can think about it as a measure of authority or trust in the graph. And the book talks about this as a method for identifying trustworthy pages. So these pages or nodes in the graph with high PageRank scores are in some sense more authoritative or more trustworthy. And really, these are just a form of identifying how important a particular node is to the graph or to our use case. But that may not be the only way that we define importance. In fact, there are many ways to define importance, and we call these metrics for importance centrality metrics. And we've already seen some of them. So at the end of the lecture last week, I talked about the hubs and authorities scores that come from the HITS algorithm, where a place like MarketWatch may have a high authority score because it has a very topic-specific set of information where lots of links lead to it, but fewer links lead out of it. In contrast, we have something like Wikipedia, where there's information about many different topics, and there's links to many other websites where people may go to. And these are two distinct kinds of importance or kinds of behaviors, and we can measure them separately with the HITS algorithm. Maybe a more direct way, and actually an example that we saw when we talked about the PageRank algorithm, was if we compare two nodes in a graph, say the Washington Post here and the New York Magazine website, we can compare them also based on their what's called degree, or how many neighbors they have. So the Washington Post has many neighbors, such as Fox News, New York Times, Raw Story, and others. And we can talk about this as a different way of evaluating importance, where we talk about importance as a characteristic of degree, where a node's degree is defined as the number of neighbors that particular node has, and we can say that the degree of the Washington Post website is much higher than the degree of the New York Magazine website, which tells us potentially something about how important the Washington Post website is to the overall network. We can see this as well in undirected graphs from our social media example of my wife and the Tennessee Volunteers, where degree is just straight the number of connected neighbors, or the number of called incident edges. We can do the same thing with a directed graph and say the in degree are the number of edges coming into a particular node, and the out degree is the number of edges originating from that particular node. And then we take the sum of these to calculate the actual degree. So we can say here for Chato Castillo's example in this graph, he has an in degree of 1, an out degree of 1, so he's following the European Research Commission account, and that account follows him. And his whole degree is the sum of his in degree and out degree of 2. Now, we talked about degree in PageRank as another way of evaluating, or sort of a naive or somewhat straightforward way of evaluating importance, where a node with high in degree may be more important than a node with a lower in degree. But this wasn't enough or sufficient for us to evaluate trust, because link farms exist and an adversary could still generate many websites or many web pages that link to a particular page. So given that, does higher in degree generally mean more importance? Or do we really only care about higher in degree or out degree specifically, not necessarily the sum of the two? And we can think about this in terms of Twitter or some social network, where you may ask it, does having more followers mean more influence than having more friends? Oftentimes you'd say probably yes. To some degree, an account that has many more people following that account than an account that follows many people, there's some difference in influence there. But that's not the only way we can talk about importance. So we've talked about now a number of different metrics in terms of PageRank, hubs and authorities. We've talked about degree. We can talk about a different kind of behavior as well. So hubs we've already seen, such as Wikipedia, but there are also bridges. So we can talk about this from a network structure perspective rather than a degree perspective, and say, well, hubs, like we've seen, have many outgoing links or links to many terminal nodes, whereas bridges have many links as well, but it's not just links randomly in the network. They actually serve as a gateway between two different groups of nodes. As we see here, this node in the middle, you might consider a bridge, and in some sense, this node, even though it may have just as many links as some other node in the graph, you could qualitatively say, well, the removal of this one node potentially has way more impact on the overall structure of the graph compared to removing any other node in the graph. So even though its degree may be similar to other nodes, in some sense it is more important to the structure. How do we define this? Can we formalize importance in some way? What does this mean? So is importance highest degree? Is it nodes that have high PageRank? nodes that are authoritative, nodes that are some combination of being hubs and authorities, or is it something else? Now, the difficulty is there is no right answer here. And we can see this if we ground this discussion in some examples from board games, where if we look at the pandemic map, if you've ever played this game, the idea is a set of virulent diseases spread across the globe, and how they spread and where they spread to is a function of how connected a particular city is. So for this example, the city of Hong Kong has a very high degree, meaning that if an outbreak occurs in Hong Kong, it'll spread to many other places, in contrast to an outbreak occurring in, say, Johannesburg in Southern Africa or South Africa, it'll only spread to 2 places. So there's some difference there in how important these 2 cities are for the spread of disease. Separate from degree, you could look at Sao Paulo and say, well, if we can somehow protect Sao Paulo, then we can cut off the spread of disease between South America and Africa. So South America is bridged to Africa through the city of Sao Paulo, meaning that Sao Paulo also has some importance. And how we use these 2 cities, or how important these 2 cities are, depends on what we are trying to do. If we know that an outbreak is already going to happen, perhaps we want to try and break bridges to keep an outbreak sort of centralized in some location, whereas if we want to minimize the number of cities that have been infected, then maybe we want to prioritize higher degree cities instead. Beyond just sort of the web mining aspect, this idea of centrality is a core question to network science in general. And there are a bunch of different ways of defining it in terms of influence, prestige, power, or control. And unfortunately, the field has sort of landed on this idea that you can't pick one. That famous sociologist Linton Freeman said there is no unanimity on exactly what centrality is or how it should be conceptualized, let alone agreement on ways it can be measured. So this is really contextual and based on your task. But we can talk about a number of common types of centrality. So we'll touch on 5 here in this lecture. The first is PageRank, which you've already seen. Then we'll talk about a version of PageRank called eigenvector centrality, then degree centrality, closeness centrality, and betweenness centrality. Let's ground this in discussion, keep this discussion in the realm of board games, and rather than talk about pandemic, we can talk about risk. Use this map to generate a graph of what the risk board looks like. And we see this graph is a relatively easy to comprehend graph. The different colors are the different continents we may look at. But already we can note that PageRank's not applicable here. And this is because PageRank, as defined in the previous lecture, works primarily for, or is developed for, directed graphs. And already we can see this graph is an undirected graph, so that tells us something different. But we can instead look at eigenvector centrality and say nodes that are high in eigenvector centrality must also be close to other nodes that have high eigenvector centrality. So this feels like the same sort of recursive definition that we described last week for PageRank. So here we can see that the Middle East has a high eigenvector centrality because it's actually pretty core to Egypt, East Africa, India, Afghanistan. It has a high number of nodes, and then all the nodes that it's close to also have some importance in the structure. Similarly to Ukraine, if you look at the risk map, Ukraine actually provides a bridge from Asia to Europe. And we talk about definitions from a formal perspective, we actually see something that's very similar to PageRank. Like I said, it's PageRank for undirected graphs, where we have some adjacency matrix, and we have some pi vector, which represents our eigenvector centrality vector, and this pi vector is in fact an eigenvector of A, the largest eigenvector. And we can calculate this through power iteration in the same way that we did with PageRank. Degree centrality we've already kind of touched on, where we say nodes that have a high degree or a high number of neighbors must have some high level of importance. We call this actually straight degree centrality. The general idea, the intuition here is that nodes with high degree centrality can reach many neighbors, or can reach the most neighbors if you have the highest degree centrality. So examples from the risk graph or the risk board, Ukraine has very high degree centrality. It's actually tied with China in terms of degree centrality, the Middle East, and North Africa. We can define this from our adjacency matrix as before, where we just sum across the columns of this adjacency matrix and say, if we have a binary adjacency matrix that says how many outgoing or incoming edges, or how many total edges there are in an undirected graph for a particular node, we just sum these up, and that tells us what the degree centrality is. And we can also normalize this to allow us to compare degree centralities across networks of different sizes by just dividing through by the number of nodes in the graph minus 1. So we know if we are excluding the idea of self-loops, or nodes that are connected to themselves, then no node can ever be connected to more than n minus 1 other nodes in the graph. In contrast to degree centrality, there's also this idea of closeness centrality. And the intuition here is that nodes that have the most shortest paths to other nodes have the highest closeness centrality. So what this means is, if a particular node, not just is it close to many nodes directly, but also the shortest path from a single node to any other node in the graph is, in some sense, the smallest set of shortest paths, or has the smallest average shortest path, then that node is somehow close to all other nodes in the graph. So you can think of this in terms of an inverse of this idea of farness, or nodes that are very far from each other, or a node that is in general far from all other nodes in the graph. You invert that and you get this idea of closeness. So again, in this risk board, Ukraine has a very high closeness centrality. We define this by talking about farness. So we can say for all other nodes beside our particular node in the graph, what's the shortest path between our current node or our target node and that node? We sum that up, and then we just invert that to get closeness. And then we can multiply by n minus 1. So yeah, this is the maximum closeness, but we can only define the closeness centrality metric for connected graphs, graphs that have paths between any two pairs of, or any pair of nodes. If we do not have that connected property, then you can only define closeness on connected components within that graph, which is very similar to some of the restrictions you get with PageRank. The last kind of centrality we'll talk about is this idea of betweenness centrality. So nodes that have high betweenness centrality are nodes that appear most often in shortest paths between any two nodes in the graph. So that means that if you have any two nodes in the graph, their shortest path somehow must flow, or is much more likely to flow between, or flow through a node that has this property of having high betweenness centrality. So this is a way of essentially identifying nodes that act as bridges. And if we look at the risk graph, we see a different structure, that rather than it being Ukraine or the Middle East, we see North Africa has very high betweenness centrality. Again, if you recall the shape of that graph, it provides a bridge between South America and Africa, and as a result, has many of the shortest paths from North or South America that flow into Africa or Asia must also flow through this particular node. We define this by looking at how many shortest paths exist between S and T. We compare this to how many of the shortest paths that exist between these two nodes must go through our particular target node V. For undirected graphs, we have a particular structure that we have to deal with where the direction doesn't matter, and we have to balance that in comparison to directed graphs. So you may ask, well, which centrality measure is best? As I mentioned, I push you to consider Linton Freeman's argument that there is no one conceptualization, instead it depends. So when I say it depends, I'll say it's generally task-driven, or what it is you're trying to do, or what your particular use case is. So we can talk about how we might use these centrality metrics from these use cases. So for instance, we already talked about PageRank and how it can be used for this ordering question, and why PageRank is superior to n-degree centrality, or degree centrality for particular types of graphs, because degree centrality alone gives too much power to an individual who can just spin up many web pages, whereas PageRank is much more distributed over the structure of the graph. Now remember, why are we doing this? We're trying to understand or provide some sort of organization on the web. So PageRank allows us to rank things based on importance, But another thing we can do is group pages, because we know, or we have some expectation, that pages that are close together, groups of pages that are tightly connected, must or are likely to be about the same kind of thing or share some kind of relationship, either structurally or topically or linguistically or something along, or socially, something along those lines, that these clusters of pages tell us something. Or if we want to understand, well, I'm on a particular page, what are other pages that are like me? You want some neighbor, and maybe some neighbor who's a few hops away. So if you look at these two circles on the graph, you may expect that random nodes from within these two clusters are similar to each other in a way that if you pick one node from one of these clusters and one node from some other place on the graph, it's less likely to be that these two nodes are going to be similar. So this is some kind of structure on the web that we may want to extract. So we have a slightly new motivation here for identifying these groups of nodes. We want to extract some structure from the web that we can use for search or to make the web more accessible or useful. And one way to do it is by grouping these nodes. So to do so, we'll introduce this idea of graph clustering and partitioning. We're given some graph. We want to identify these groups and have an algorithm that can say, well, these are the different sets of nodes that exist in our graph, and they should be grouped together somehow. And there are two ways of doing this, like I mentioned, partitioning and clustering. So partitioning is generally where you want to split some graph into some predefined K sets, where the sets are expected to be of approximately equal size. And the primary metric you're looking for here is minimizing the number of cuts you have to make to the graph, how many edges you essentially have to delete or break in order to separate this graph from one partition from the other. Clustering, however, doesn't necessarily have to have a pre-specified K. Instead, the similarity idea, or the structure around clusters, doesn't necessarily have to be built by the number of edges that you cut, so much as we expect clustering to capture some idea of similarity. And similarity may not be directly available to us within the graph, but we hope that by building these clusters or extracting these clusters, we have some proxy for similarity that has some real-world meaning to the nodes in the graph. So the obvious answer, or the obvious example of this that I've shown you already, is clustering the graph into Democrats and Republicans, where two nodes that are in the same political ideology cluster are likely to have similar political ideals, whereas a node taken from one cluster and compared to a node from another cluster may have very different ideological positions. So how do we define this? From a rigorous perspective, we can say the clustering task is really two pieces. The first is to maximize the number of within cluster edges, and the second is to minimize the number of between cluster edges. Now the second piece is really the goal of partitioning that I mentioned, so we want to minimize the number of cuts, but also something additional to clustering is maximizing the number of edges that exist within a particular cluster. Then the question becomes, how do we measure how good that clustering is? Or can we say whether one clustering is better than another? And there is in fact a metric for this called modularity. I'm not going to go deeply into this. I want to just introduce what it means, because we'll talk about it in terms of application here in a minute. But this is the general optimization characteristic for modularity, where we have this metric defined for the entire graph. We have factors k sub I, which is the degree of a given node k, and m is the number of edges in the entire graph. Then we can say we'll break this modularity question down into some del that is 1 if and only if vertex or node x sub I and node x sub j exist in the same cluster or the same group, and it's 0 otherwise. We then use that to weight the combination of how many, or whether there is an edge between these two nodes, x sub I and x sub j, which we extract from our adjacency matrix. This aij tells us whether there is an edge between I and j. And then for that edge weight, we then subtract off how likely is it that these two nodes would have been connected based solely upon their degree. The idea being that nodes that have a very high degree are going to be connected to many other nodes, not because of some internal structure or similarity between those two nodes, so much as just the random statistical probability of being connected having high degree. So instead, with modularity, the idea is adjacent nodes that have few edges. So these cases where we don't have many edges to many other nodes, if two of these nodes are adjacent, then they ought to be in the same cluster. Now, how do we do this, or how can we leverage this method or this metric to identify these clusters? We can go to betweenness centrality and say, well, how about we just remove nodes, or rather remove edges that have high betweenness centrality. So we'll slightly modify the betweenness centrality aspect. Instead of talking about nodes and their betweenness centrality, we can talk about edges and their betweenness centrality. So then we can take a given graph and iteratively remove edges that have this high betweenness centrality characteristic. That is, edges that exist in many shortest paths. So here in this sort of bow tie graph, you might remove these edges from, or that are incident to, this one node that has a very high betweenness centrality. And we stop removing edges when our modularity metric for the entire graph reaches some threshold or has reached some maximal value. So you can imagine if this is the graph, or some example graph we want to look at, we can iteratively remove, say, the top 10 edges with the highest betweenness centrality and see what the modularity is, or calculate the modularity for that particular graph. So after the first 10 or first 11s, I guess, we see a rapid peak. But if we keep removing these edges, then we see some secondary peak here after about 25 or so edges. And then after that, we see a gradual degradation of modularity for the rest of the number of edges that we remove. So we can make some claim or estimation that removing the top 25 highest betweenness centrality edges gives us a good set of clusters for this particular graph. NetworkX, the Python package that I mentioned and have an example for in the GitHub repo for the class, has an implementation of this particular method of identifying communities in graphs already. So remember, what is the goal that we're trying to do? We're using the Girvan-Newman method and this idea of betweenness centrality to break a collection of web pages and their connections to each other into these groups, because we have some expectation that two pages that are within the same group are going to be similar in some way. So we use the Girvan-Newman method to do this, but there are other ways that we can do it as well. So before I get into those, let's briefly go through a detour where I'm going to break a rule that I told you about last time. So in the previous lecture, when I talked about how we can represent graphs and what graph structures look like, I said if you're given some graph with some vertices and edges, generally all the vertices in your graph should be the same type of thing, same type of entity. As all rules are made to be broken. And we can say, well, if we want to have a graph that has multiple types of nodes, there's an existing graph construct out there called bipartite graphs that do this for us if we have two types of things that we want to model. There are a couple of other constraints for bipartite graphs as well. And in fact, there's a generalization of bipartite graphs called k-partite graphs that have k different types, whereas bipartite graphs have 2 different types. Now, the additional constraints that I'll mention is if we have some graph and it is structured as so U2 is connected to vector or to node or vertex V3, V3 is connected to vertex U4 or node U4, and so on. For a bipartite graph, we have graphs that must be separable into 2 types of nodes. When we talk about node types, we can talk about sets of nodes, that a single node must only be of one type. So the types let us separate our graph into 2 disjoint sets of vertices, and no nodes of the same type are ever connected to each other. So that's the additional constraint we have here, and this is what this looks like for a different way to visualize these 2 graphs, where we have all the nodes in set U and all the nodes in set V, and none of the nodes in U are ever connected to each other, none of the nodes in set V are ever connected to each other. The only connections that exist between nodes in different sets. So another way of interpreting this is all these nodes in the top row are type 1, all these nodes in the bottom row are type 2, and you can only have connections between types. So some examples, some real-world examples. There is a very popular method for doing residency placement following med school, where you build a graph of nodes that represent residents and hospitals. And residents are only ever placed in hospitals. Residents aren't placed in each other, hospitals aren't placed in each other. So in this kind of structure, it makes sense that residents and hospitals can only ever be connected to each other. And you can have this idea of some resident-to-resident relationship. Say 2 residents went to the same hospital, or 2 med students had the same residency, but it has to exist or be mediated through a particular hospital. You can do the same thing with dorm rooms, saying 2 students are co-located because they share a dorm room. Now, you may have a separate graph of relationships between students based on whether they were roommates, that you could construct with only a single type. But this bipartite structure has these 2 separate nodes of type student and type dorm that are connected to each other, but never within the same type. And there are a number of other examples as well. So there's the author link graph, where we have 2 types of nodes being authors and the places they write for. So authors write for newspapers. Authors don't, you could imagine authors write for other authors, but for a bipartite graph, you may say authors write for particular newspapers and news organizations. And that's where the edges come from. The web link graph for social networks, you could say, well, a user in Twitter or a user in Facebook shares a link to a particular web page or a particular YouTube video. And generally, users don't share links to other users, though you can. That would be a different kind of structure. Or a product graph on Amazon, where a person buys a product. Generally, people don't buy people and products don't buy products. So all of the interaction occurs between these 2 types. Or a movie review graph, where a person is reviewing a movie. Movies don't review review other movies, and people don't review other people in this particular context. So when we talk about looking for groups of nodes, we can extend this to groups of nodes in a bipartite graph. So I showed you the Girvan-Newman method that looks for groups of nodes that you might use for finding web pages that are about the same topic. Now you can apply, or we want to be able to apply this kind of method and extract groups of nodes in these bipartite graphs where there is some sort of relationship or structure between or within these groups. So how do we do this? We can do this using random walks and what we talk about, or what the book has in the last bit of chapter 10 that I asked you to read about Simrank, which follows directly from our concept of PageRank. So remember, PageRank is a conceptualization about the likelihood of randomly falling on or walking to a particular page in a network. So if we started at many different random points in the graph of the web, and we sort of randomly followed these links, or you randomly clicked links on a page, where are you most likely to end up? And that likelihood is proportional to your PageRank for a particular website or a particular web page. So YouTube is it's a web page with a high PageRank score, meaning that if you if you showed up on some random page on the internet and clicked around, you would eventually land, or you're much more likely to eventually land on YouTube, as opposed to potentially landing on Etsy or potentially landing on Reddit. You're much more likely to land in these places than you are one of these terminal nodes that has very few pages linking into it. So if we take the web structure that we have, that we've already seen, and say we want to make some slight constraint to the PageRank approach that we had, what does this allow us to do? So if we want to understand how similar or what a particular group of nodes may look like, the PageRank algorithm only tells us this global kind of structure. How likely are you to land on a particular page given starting anywhere in the graph? But what if we constrain that to say, well, rather than starting anywhere in the graph, what happens if we start from a single node? So we look at a specific node in the network. We can make some assumption based on this example structure here that if you do these random walks away from this one particular node, you're much more likely to land relatively close to that node than you are to land very far away. This satisfies this idea of similarity that we're looking for. We want to be able to group nodes into clusters that are capturing some idea of similarity, and nodes that are close to each other. Maybe they're not direct neighbors, but somewhere relatively close. You can think of this from a social network as a friend of a friend kind of relationship, are probably closer to or somehow more similar than nodes that are very far away from each other in the graph. So how do we do this? Is there a way where we can modify the PageRank approach or the PageRank algorithm that we talked about last time to give us this ability to focus on a particular starting node and then construct a vector that tells us not the likelihood of appearing on this page or landing on this page from anywhere in the graph, but the likelihood of landing on this particular page or this particular node if we started from one specific target node. So if we recall the PageRank definition, remember we have some adjacency matrix A. We can slightly modify this into a stochastic adjacency matrix by dividing each column by the degree of the node associated with that column. So we get this transition matrix M. Remember that the columns must all sum to 1 because that gives us this stochastic characteristic. From the PageRank idea from last time, we talked about this idea of power iteration, where we take a vector, we multiply it by this transition matrix many times through this process of power iteration, and then we land on, or the resulting vector that comes out at the end is our PageRank vector, or the vector associated with the highest eigenvalue of the graph, of this directed graph. So how can we convert this algorithm into a method for creating a similar kind of vector given a specific or constrained source node? Well, we can make two modifications. The first one is to add what we call a teleport edge that allows the transition or the random walk throughout the network to go from anywhere in the graph back to that source node. So here we say we have some teleport edge with some that allows you to go back to that source node with some probability 1 minus beta. That is, you have some probability beta of continuing on your random walk throughout the network. We can modify this transition matrix slightly for focusing on, for example here, we'll focus on node A in the graph. We'll modify this transition matrix by multiplying all of the edge weights in the stochastic transition matrix by our beta value. Remember, this beta is the probability of continuing this random walk throughout the graph. And then we will add the source node transition from all nodes back to the source node. So we just add this 1 minus beta transition for the row A, which says, if you convert this back into a node edge diagram, that between every node in the graph and our source node A, there is some additional transition, some additional edge that goes from, say, node B back to A with some probability 1 minus beta. By adding this in, now we have preserved this stochastic structure where the sum of each column is 1, and we can go back to the power iteration method to make our second modification. So remember, for PageRank, the initial idea was we start with a vector that has uniform likelihood or uniform probability of showing up on any graph or on any node in the entire graph. So we have 1 over n is the initial values in our vector. Let's restrict that to being just starting on the source node. So we have our source node A, the value in our initial vector R is 1 for that source node and 0 for every other node in the graph. So that says starting on this one specific node. Then we can apply this power iteration method in the exact same way with the slight modification of what this transition matrix looks like. And in the end, after enough iterations, this RT plus 1, this iteration on R, converges to the likelihood of ending on any particular node in the graph, starting from the source node A. So this becomes not our PageRank method, but the Simrank method that's presented in the book. So now we have a new vector, R, our Simrank vector, that will have high weights for nodes that are nearby or near to our source node. So this node, or this additional node here, has high Simrank because it's relatively close to the source node, meaning it's much more likely, you're much more likely to end up on that node with many random walks throughout the graph, compared to some node very far away that's going to have low Simrank. This is exactly the structure that we wanted in the metrics that we're looking for. So now we can use this Simrank vector for all source nodes in the graph. So say R sub A is the Simrank vector starting from node A, R sub B is a Simrank vector starting from node B, and so on. We have these column vectors for every source node in the graph, and we can push all of these into a matrix that is a V by V similarity matrix, where we have a square matrix where every cell in the matrix tells us the likelihood of showing up on that particular node in that row if we had started on the node represented by that column. Now we can easily apply some sort of k-means or other clustering algorithm onto the similarity matrix, and that will give us a set of clusters of nodes that are more similar to each other than nodes outside of those clusters. So this gives us a way to find groups of similar nodes in a graph, which leads us very nicely into what we want to talk about next time. So in Module 3, in Chapter 3, we'll talk about finding similar items. So how we can talk about new ways to identify what similarity means. So here in this case for the graph, similarity means how likely are you to show up or land on a node that's close by the source node. But you can talk about similarity in terms of images. Do two images look similar? They have the same kind of objects in them or the same color palette. Two pages are similar on the web if they contain similar texts, but also if they are close together or they come from the same domain. There are lots of ways to define similarity, and we'll talk about that, or we'll continue that discussion next module. So now that this rounds out the Module 2 lectures, for this particular lecture, you should now be able to describe at least 3 network centrality metrics. So we've talked about PageRank and eigenvector centrality. We've talked about degreed centrality and betweenness centrality and closeness centrality. You should be able to use the Girvan-Newman method and betweenness centrality, apply that to a graph to iteratively remove edges that have high betweenness centrality until you end up with some set of clusters or groups of nodes in our graph. You should be able to construct bipartite graphs and be able to identify or define, what are the constraints on bipartite graphs. And then you should be able to explain how we use random walks that we used for PageRank applied to these, especially bipartite graphs, to generate some idea or measure of similarity in a particular graph. When we create the Simrank vector that tells us how similar two nodes are, if we started on a particular node, to the likelihood of ending on another node. All right, so if you have questions about any of this, post in the Module 2 discussion forum. I encourage you to explore some of these techniques in your Module 2 homework. Many of these techniques are already implemented for you if you're using the NetworkX package in Python, so you don't have to do heavy lifting for implementation, but I encourage you to explore using them to evaluate or explore or analyze the graphs that you've constructed.